Okay, so let's continue. So it's a pleasure to have David telling us about conformal field theory.
All right. I put a list of some resources up. The first one that you guys should definitely look at are these lectures by Slava Richkov. He does something very similar to what we're going to do here. He starts from the basics, introduces conformal field theory, describes the structure of conformal field theories, and ends with the conformal bootstrap. And I'm going to be following what he does pretty closely, although this is a condensed version of that course. There's a big reference by DiFrancesco and others, a big yellow book called Conformal Field Theory. And the first few chapters of that are on higher dimensional conformal field theories, which is what we're going to be interested in. And also a very important reference that I hope many of you have had experience with is Polchinski. In particular, there's a really nice appendix on path integrals, and we'll be using a lot of path integral methods in this course, and I really recommend his discussion of them. And he also has some nice discussion of similar methods in Chapter 2, where he talks about 2D conformal field theories, and a lot of what we talk about will mirror that discussion also. So I recommend that you take a look at these references. Okay, so what is a conformal field theory, and why are they interesting? So it's a generic phenomenon that if you take a quantum field theory and you zoom out and look at very long distances, then the theory becomes scale invariant. And the reason for this is just that you're looking at very long distances, so or equivalently low momenta. So all those mass thresholds that Raphael wrote before are effectively all at infinity. All the masses are gone. There are no mass scales in the theory. And so the theory becomes scale invariant. Sometimes it's a very boring theory. There's nothing in it. But sometimes it can be interesting. Another generic phenomenon is that if you have a local theory that's scale invariant, then very often, in a huge class of examples, it's actually invariant under a larger symmetry group, namely the conformal group. So a conformal transformation is something that locally looks like rescaling plus a rotation, but it can be different at different points in space-time. And if the theory is sufficiently local so that a given point only cares about its nearest neighbors, then this can often be a symmetry as well, assuming scale invariance is there. So a good model for a quantum field theory, and I should say this would be a UV complete quantum field theory, is as a renormalization group flow between a CFT in the UV and some CFT in the IR. So the argument for the UV is that if you have a UV complete theory and you zoom into very, very short distances, then again, all the mass scales that were present effectively go to 0 instead of infinity, and they also don't matter. So you should have a CFT. We'll return to that in a second. That's obviously a big assumption. But this is a good model for a quantum field theory, and many quantum field theories can be described in this way. And so it shows immediately why studying conformal field theory is important. It's because by understanding conformal field theories, we understand the beginning and endpoints of renormalization group flows. And this gives us a way to map out the space of quantum field theories. So the strategy will be to understand the beginning and end of these flows as much as possible. And when we understand them very well, then we can work our way towards uncovering the full structure of the theory. This is a many decade-long program, and today I will not be completing this program, but just talking about the very beginning steps. A good example to keep in mind, is phi-4 theory in 3 dimensions. So this is an action with a mass term and a phi-4 interaction. This is a quantum field theory that is the free boson in the UV. So UV, it's the free boson. And the reason is that in 3 dimensions, the canonical dimension of phi is 1/2. So G has mass dimension 1. So at very, very high energies, G is effectively 0. And you can just treat it as a free theory. M is also effectively 0. In the IR, well, there are 2 different things that can happen. So for generic M, it's the trivial theory. By which, so by trivial CFT, I mean it's a massive theory. So the particles have masses, and if you keep zooming out to even farther and farther and farther distances, you should integrate those out as well, and you're left with nothing. But there's something more interesting that can happen, which is you can get a non-trivial CFT for some special value of m squared. Okay, so you set up this Lagrangian. You have to tune the mass appropriately, and when you do, you'll end up with some non-trivial theory in the infrared. It is extremely difficult to study this theory using traditional techniques. And the reason is because the coupling constant, as I said, has dimensions of mass. So perturbation theory, let's see. So perturbation theory gives an expansion in g times x, where x is some distance scale. And if you're zooming out to very, very large distances, this expansion breaks down when x is much bigger than 1 over g. Okay? So in particular, getting access to this theory and doing computations in it is basically, well, it's very difficult starting from this picture. And in fact, the best thing that we know how to do in this picture is start in 4 minus epsilon dimensions, where the theory is weakly coupled, and then do a bunch of computations, 5-loop computations, and then set epsilon equal to 1. And this works way better than it should, which is amazing, but it's also obviously conceptually problematic. So another important example is the 3D Ising model. Actually, we'll also be talking a little bit about the 2D Ising model. And so what is this? This is something that you probably learned about in your thermodynamics class. You just take a lattice of spins. So you have a bunch of spins. These are classical spins. So SI take values in plus or minus 1. It's just a classical statistical system, so we're usually interested in the partition function, which is, so it's a sum over all the spins, all the possible values of the spins. The theory has nearest neighbor interactions. So by this notation, I just mean that I is next to j on this lattice. And the interaction is just SI times Sj, and there's some overall coupling, capital J. And you can think of this as a discrete path integral usually, in the case over here, we had this field phi takes points in Rd, where d is 3, to real numbers. And there we do the path integral in sum over phi. Here we have that these s's take lattice points essentially to z2. The fact that this is a path integral means that it has a lot of the same properties that this theory has. In particular, if you have the path integral over some region, you can cut the path integral and talk about states living on spatial slices. You can glue path integrals together and do all sorts of computations. Here, that language is you can consider the partition function where you fix some spins at some level here and fix some spins at some later level and do the partition function over everything else. And basically what that does is it computes the transition amplitude from this set of spins to this set of spins. We'll talk more about that in a second. So this is a discrete classical system, but in the continuum limit, it becomes a quantum field theory. And actually, for some special value of j, it becomes a non-trivial conformal field theory. And amazingly, it's the same one as phi-4 theory. This is pretty incredible. So we're used to writing these actions down and then treating them perturbatively because that's the only thing we know how to do in most cases. But actually, this gives a completely rigorous, explicit definition of a conformal field theory. This is something you can do on a computer. You put it on a computer, and it's a very well-defined process. You take the lattice spacing to 0, you adjust J appropriately, and you compute correlation functions. So it's completely non-perturbatively well-defined. And the fact that these things are equivalent is pretty amazing. OK, it means that we should amend this picture a little bit. So instead of some CFT UV, we could have some other microscopic system that also flows to some CFT in the IR. And this is definitely an interesting thing because this is what happens in nature. So this same CFT shows up in water, the phase diagram of water at the critical point. So that's certainly not a nice discrete lattice theory. It's an extremely complicated theory with water molecules interacting via all sorts of interesting forces. But the same theory pops out at low energies if you tune the temperature and pressure appropriately. And it also shows up in magnets. So we say that all of these theories are IR equivalent. This is sometimes also called critical universality. Or sometimes high-energy theorists like to call it duality. So you might have heard about Seiberg duality, which is a duality of exactly this type. It's just an example of IR equivalence. So the problem is that in any of these descriptions, computations are not easy. The lattice model is probably the easiest. You can definitely put it on a computer. But there are limits to how well you can do for many interesting computations. So the other thing we should notice is that this non-trivial CFT is interesting, and it somehow doesn't care about the UV theory that we started with that flows to it. So a better idea is to try to characterize this CFT itself without using any particular microscopic description. And that's the Bootstrap philosophy. It's actually a concrete strategy. So the first observation is that we should focus on the CFT itself. And this is very much in the spirit of the effective field theory techniques that Raphael is talking about, except sort of taken to the extreme. And then what should we do? Well, so we should determine the full consequences of symmetries. And impose consistency conditions and if we rely only on these two things, then we can hope to get non-perturbative information. In some cases, this information is so constraining that we can actually solve the theory. And this is particularly true in two-dimensional conformal field theories. In higher dimensional conformal field theories, it was not believed for a long time that this strategy would work, at least to do anything non-trivial. But actually, one of the amazing things that we've learned in the last 7 or 8 years is that you can make a huge amount of progress with this strategy, even in higher dimensional CFTs. And that's something that's basically the goal of this course, to talk about how that works. And I should say, so this is a good strategy for this theory because we're going to try to make the most use possible out of the symmetries. And basically, none of the microscopic descriptions do that. They don't have conformal symmetry built into them. It's something that has to emerge. We're going to assume conformal symmetry. There are some cases in which this is really the only thing that you can do, the bootstrap. And so I should maybe add another thing, which is that you can have something completely wild and unknown that flows to some CFT in the IR. So as a particular example, you could take the theory of the effective theory living on a stack of M5 branes in M theory. We know very little about this theory. We don't really have a microscopic description of M theory. There's no Lagrangian. But by sort of the effective field theory logic, this stack of M5 branes is also described by a CFT at long distances. And if we're only relying on these basic principles, we can actually try to describe that CFT and put constraints on it. And this is an active area of research. So there exist quantum field theories that don't fit into the usual perturbative paradigm, that don't have this nice microscopic description, but we still believe make sense. And the bootstrap is a way to try to compute and define these theories. And so that leads me to sort of the most ambitious goal of the bootstrap, which I feel almost, it's extremely ambitious, but the hope is that you could one day use these kinds of principles to just give a definition of quantum field theory that's completely independent of Lagrangians, and get rid of the need for relying on a Lagrangian, and allow yourself to work non-perturbatively. So that's the sort of big goal that you should have in mind for the Bootstrap program. And there are lots of open problems in working towards this goal, and I'll try to point out some of them. Okay. Good. Any questions? Yes?
The flow to the IR is
So you can't. So the CFT in the IR has basically forgotten everything about the microscopic theory it came from. You can model the effect of having some UV theory by putting irrelevant operators into the CFT. So that means that if you're just looking from the point of view of CFT, if you're here and looking up, you know that there will be irrelevant operators that are going to 0, and you can describe their effects in the CFT. I can talk a little bit about that at some point if you like. But yes, that's sort of the whole point. So if you really want to understand all conformal field theories, all quantum field theories, you should really focus on trying to describe what all of these could be. And from there, in principle, you can do the RG flow and not lose any information. Other questions?
So I have to, I'm an old guy, so I have to object to your program because there are a lot of not formal or are boringly conformal.
Well, I like free particles. Those are perfectly happy conformal field theories to me. You're right. So there exist interesting theories that are not UV complete. For example, a theory with an effective theory of gravity. So the Standard Model coupled to general relativity, and those do not fall into this classification. So for there, you have to use ADS-CFT or DS-CFT, and then you are talking about a CFT. But that's probably beyond. That's next week. But I totally agree. This is this is a way of defining UV complete quantum field theories. Other questions? Okay. All right. So step one. I hope I've already convinced you of step 0, that we should focus on the CFT itself. Step 1 is to look at the consequences of symmetry. The starting point for this is the stress tensor. So a local quantum field theory should have a conserved stress tensor operator. So it satisfies this equation. And this holds as an operator equation. By which I mean it's true as long as t of x doesn't coincide with any other operator insertions in the correlation function you're computing. So the more proper thing to write is a ward identity for correlation functions of t mu nu. So we have t mu nu and a bunch of operators. And let's say we're interested in computing this correlation function. So we compute the correlation function, we take the divergence of t, and the ward identity says that this is equal to a sum of delta functions times derivatives of the operators. Okay, so this is a consequence of the Noether procedure. And you can derive it. I won't do the derivation here, but it's a standard thing you can find in QFT textbooks. And it's completely consistent with this operator equation. If t is not at any of these points, x1 through xn, then the divergence is just 0. So when we have a ward identity like this, it's natural to integrate it over a ball. So let's suppose we have our operator insertions, which are some points, and we pick a ball B that encloses some of the operators, and I'll call the boundary of B sigma. So that's this thing. So just taking this equation and integrating it over the ball, we get that an integral over sigma of a correlation function of t mu nu is a sum over operators inside B of derivatives. Okay, so I said we're talking about symmetries. Where do symmetries come in? So it's natural to define this integral of t mu nu over a surface. So I'll put in a conventional factor of minus I. So let's define this to be something called p nu, and it depends on the surface sigma. The statement of this word identity is that a correlation function of this thing with a bunch of operators O is equal to a sum of derivatives of things that are inside sigma. In particular, it doesn't really matter on the shape of sigma. So we say that this operator is a topological surface operator. Okay, so if you have a bunch of local operator insertions, you can insert p of sigma into the correlation function and compute something, or you can compute it with some other surface sigma that encloses the same operators, and you'll get the same answer. So it just depends on the topological class of this surface. We can move, so this means we can move sigma freely as long as we don't cross any other operators. Okay, so this is all very natural to do in a path integral. It follows automatically from conservation. So let's interpret this in terms of quantum mechanics. So this leads me to the notion of quantizing a theory. So the idea is that a quantization is different quantizations give different interpretations of one path integral. So this is something that is totally familiar to you guys from Lorentzian invariant quantum field theories. If we have some path integral, we can think of spatial slices as we can pick some reference frame so that we have these spatial slices, and then think about the Hamiltonian as evolving us from one spatial slice to another. But if we're in a Lorentzian invariant theory, and I should say that I'm going to be working in Euclidean signature for all of my lectures. So by Lorentzian invariant, I mean rotationally invariant. Okay. All of the theories I talk about, you can Wick rotate between Euclidean and Lorentzian signature, but I'm not really going to have time to talk about the consequences for Lorentzian signature in this course. So we'll just think about Euclidean theories. But this is something you can do. You can think of this as the space direction, and that's the time direction. You can write states here and involve them with the Hamiltonian and so on. But in a rotationally invariant theory, you can also pick some other spatial slices and think about evolving the theory that way. The same correlation function, the same path integral, gets interpreted as an expectation value of a time-ordered product of operators. And I'll be explicit now about their times. In some vacuum state. And the state that you start with, the Hilbert space that the state lives in is different. The Hilbert space associated with this slice is different from the Hilbert space associated with that slice. And the time ordering is different. Obviously, if you have some collection of operators here and you order them with respect to this time, they could have a different order with respect to this time. Okay, so you can think of this as sort of the underlying object. And what we're doing here is we're breaking this object up into a piece of path integral here, another piece of path integral here, another piece of path integral here, and just interpreting it in terms of quantum evolution in different ways. Any questions? Okay, so this looks hopefully familiar and is maybe even a bit boring, but we're going to take this idea in a really interesting new direction, probably next lecture. So these are good ideas to have in mind. And it allows us to talk about the relation between these topological surfaces and symmetries. So first of all, let's take this same picture. Suppose we have a bunch of operator insertions in our path integral, and we insert at some time. So this is sigma sub t1, some surface on a spatial slice at time t1. We insert this operator, this topological surface operator there. Because the operator is topological, it's the same as if we insert it here at some later time. So this means that as long as we are careful about not crossing any operator insertions, we can just neglect to write the actual surface, sigma, and just write p nu. Okay? So when we write p nu, we should be careful to keep in mind the topological class of the surface it lives on, but we can forget which surface it lives on. And basically what we've derived here is that this operator p nu, whether we act on the Hilbert space at this time or the Hilbert space at this time, it gives the same answer. P nu is called momentum. And this fact that it's topological is conservation of momentum. Okay, so these topological surface operators correspond to symmetries. Okay, so what happens if we do move, if we do try to move p nu past an operator? So let's suppose we have some operator here, O of x. In the middle. And let's consider a difference of an insertion of p mu at sigma at time 2 and p mu on sigma at time 1 with O of x. So first of all, how does this get interpreted in a quantization of the theory? Well, because of time ordering, when we have sigma of t1, we have to insert the operator p first. And when we have sigma of t2, we have to insert the operator p last. So this actually becomes a time-ordered product of a commutator of p mu with O of x. And then there could be other operator insertions. Okay, so this is the path integral version of a commutator. And because it's topological, we can do something neat. So we have, let me just redraw it to give myself a little bit more room. We have the operator O of x in the middle here. And we have these insertions. This one, I'll draw some little arrows to indicate the orientation. And because we have a minus sign, we should think of this surface as being oriented oppositely. And now, because these surfaces are topological, we can deform them. So let's take them at infinity and squish them together. where they cancel each other, and here squish them together where they cancel each other. And you can see that you can deform this to a single surface, sigma prime, that surrounds O. So this is equal to P mu of sigma prime with O of x. And what is this? Well, here we can just use our word identity, which says that if we have the integral of T mu nu over a surface, the surface surrounds a bunch of operators, then it just gives us derivatives of those operators. So this is equal to I derivative O of x with other operator insertions. And this is just the word identity. Okay, so to summarize, we can just write something that you all have seen and know and love, which is that the commutator of P mu with O of x is just I times the derivative of O of x. And the reason I went through all this song and dance to derive this simple equation is that it makes it clear that this equation makes sense and is true in any quantization of the theory. Okay? So this trick of taking these slices and deforming them so that it's just a circle around O, it obviously doesn't care about which direction we chose for time. I could have chosen this as the time direction. I would have done the exact same computation, ended up with a surface surrounding O, and I would have had the exact same thing. So even though this statement, simply writing a commutator, looks like it's making reference to a way of quantizing the theory, it actually is something that we can make sense of without thinking about a particular quantization. So this is true in any quantization. And whenever you see a commutator, you can just think about surrounding the operator O with some topological surface in the path integral language. This equation can be integrated to give O of x is e to the minus I px, O of 0, e to the I p dot x. And this is also true in any quantization of the theory. Writing something like this with operator ordering looks like it's really talking about a particular quantization because in path integrals there's no sense of ordering. But even though it's written in that language, it's true in any quantization. So you can really think of this in path integral language as surrounding O now with the topological surface operator that is the exponentiation of this topological surface operator. Questions? Yes? No. So I haven't used conformal anything yet. This is true in any quantum field theory. That's a great question, and that will come soon. Other questions? Good question. So one way to derive this word identity is by demanding diffeomorphism invariance of the theory. And if there's an anomaly, the word identity will be modified, and you have to keep track of that. Other questions? Okay. Now I see why Raphael was using the Okay. Good. So we didn't use any conformal symmetry. So if we have more structure, there's obviously more that we can do. So in general, if we're given some vector field, I'll call epsilon, then we can define a charge q of epsilon associated with some surface sigma as an integral over sigma of ds mu epsilon nu t mu nu of x. And this charge will be conserved if this current is conserved. So d mu of epsilon nu t mu nu equals 0. So what is this? All right, so d mu can hit epsilon nu. If it hits t mu nu, derivative of t mu nu is divergence of t mu nu is 0, so that's just 0. And we should also use that t mu nu is symmetric. So this is 1/2 d mu epsilon nu plus d nu epsilon mu t mu nu. Okay, so the condition for conservation should be that this is equal to 0. And this says that epsilon is a killing vector. Or an isometry. Okay, so we already talked about one of the solutions, which is just epsilon is just that, which generates a translation. And I'll distinguish, it won't be that important, I'll distinguish between the conserved charges, q sub epsilon, and the vector fields by writing the vector fields with lowercase letters. For p, it will be a little bit hard to tell, but hopefully this won't matter too much. So this is one solution to the killing equation. Another solution is this. And this just generates rotations. Okay, and in general, that's all we have. But in a conformal theory, we can say more. And the reason is that there's an additional condition on the stress tensor besides simply conservation. So in a conformal theory, the stress tensor is also traceless. And again, this holds as an operator equation. Which means it's only true when inserted away from other operators. In general, there can be contact terms, and there is indeed a word identity for the trace of t mu nu. But we'll dance around that word identity a little bit. We're not going to need its explicit form for a while. And one way to interpret this is it basically means that the theory is insensitive to changes of the metric that are proportional to the metric. Okay, the stress tensor measures the response of the theory to a change in the metric. If you change the metric by something proportional to the metric, then it brings down the trace of the stress tensor. Yes?
Sometimes people talk about proof vector and make it tensor traceless or symmetric.
Right.
What is the exact
The exact statement is that there exists an operator that is conserved, has spin 2, and traceless in a conformal theory. Improvement terms just mean that there are other operators in the theory, and you can take linear combinations of different operators. And if you have a spin 2 operator that isn't traceless, you're just looking at the wrong one. Okay, so now we can relax the condition on epsilon slightly. So here we just demanded that this is 0, but actually, if the stress tensor is traceless, it's enough to just say that d mu epsilon nu plus d nu epsilon nu is equal to something times the metric, where that something is a scalar function that can, in general, depend on x. Okay, so if you have this, then just pop it in there, and trace the stress tensor is 0, so you're good. You get another conserved quantity. And this is the conformal killing equation. And by the way, by just taking the trace of both sides with the metric, you can see that you can solve for what C of x is in terms of epsilon. So it's not actually an independent quantity. I'll leave that as an exercise. And this has some extra solutions. So in addition to translations and rotation, there's dilatations. Which I insisted on calling dilations for a long time because that's actually a word and dilatation isn't a word, but everyone says dilatation, so that's what we're going to say. And then these slightly more interesting ones, special conformal transformations. And now is the time to note that in 2 dimensions, there are an infinite number of other solutions, leading to an infinite set of conserved charges. And this is totally awesome and great. And we won't have time for it in this course, but this is a very old subject, and it's very well treated in the resources that I listed. But these solutions that I've written down explicitly exist in any space-time dimension. And let me just give you a quick sense of what's going on here. So translations and rotations are obviously familiar. Dilatations, this is just the vector field that generates rescaling of x by some quantity. Special conformal transformations are a little bit more interesting. So exercise, and no one's going to check that you do the exercises, but I'll list them. I'll list a few of them throughout the lecture. So verify that D and K solve the conformal killing equation, and show that K mu is I P mu I, where I is an inversion. So I takes x mu to x mu over x squared. So basically what an inversion does is it takes all the points outside the unit sphere and it shrinks them inside the unit sphere. All the points inside the unit sphere, it maps outside the unit sphere. And an inversion is actually a conformal transformation. And so the meaning of this equation is that you can think of special conformal transformations as translations around the point at infinity. So the usual translation moves the origin, and fixes infinity. And a special conformal transformation is exactly the opposite. It fixes the origin and moves infinity. And those were fuzzy, fuzzy words, but this is the precise meaning of that. Good. OK, so we have a bunch of conformal killing vectors. They give us a bunch of conserved charges. And this gives us the conformal algebra. Which says that a commutator of two of these conserved charges with different conformal killing vectors is equal to the conserved charge associated with the commutator. And this is actually a non-trivial claim. It's something that you have to check, and I'm not going to prove it in lecture. But actually, I should say it's violated in some interesting cases. For example, in 2 dimensions, with this infinite set of conserved charges, it's not actually true that the conserved charges give an exact representation of the Lie algebra of vector fields of conformal killing vectors. They actually give a central extension of that algebra. And this is related to the fact that Raphael mentioned that you can have projective representations of your symmetry groups instead of just normal representations. It turns out that this algebra of vector fields does not admit an interesting central extension. So it just so happens that this is true. Okay? But for now, we're just going to assume that it's true. And look at the consequences. And I should also say that when I write this equation, again, it's true in any quantization of the theory. I'm writing a commutator. It looks like I'm talking about a particular quantization, but it's true no matter what for the same logic as before with this here. And in path integral language, you can think of this commutator as just telling you how to move topological surface operators past each other. OK, so what is the form of this algebra? So let's start with the more familiar parts. So we can just compute these commutators of charges from the commutators of the vector fields. So rotations, we already know the answer. This just gives the algebra of SOD rotations, and I won't even bother to write the explicit commutation relations. You've seen them all before. And similarly, a commutator of mu nu with p rho is just the following. And this just says that p is a vector under SOD. And this looks basically the same because k is also a vector under SOD. Okay? So that's just simple. Those are just the consequences of rotations. How is the legibility? Is it OK with all the stuff underneath? OK, good. All right, so the more interesting commutation relations are these. Okay, what do these mean? So we'll see a little bit later that the eigenvalues of D are of the form I times delta, where delta is a positive real number, called the dimension. So what this equation means is that P mu, momentum, is like a raising operator for dimension. If I have some state, I act with P mu, it has higher dimension by 1 than the original state. And similarly, K mu is a lowering operator. So raising, lowering for delta. And this one is also interesting, although a little less easy to interpret. Basically, K mu generates these translations around infinity. It's some interesting non-translationally invariant vector field. And its commutator with P mu is non-trivial, and they give D and M. And there's a nice way to arrange the conformal algebra that's useful to think about, which is just according to scaling dimension of the various generators. So by which I mean their eigenvalue under the adjoint action of D. So basically the eigenvalue that appears here on the right of a commutator with D. So we have P mu, which is eigenvalue plus 1. We have D and M mu nu, which have eigenvalue 0, and K mu, which is eigenvalue minus 1. So P mu is dimension 1, K mu is dimension minus 1, and these two guys are dimensionless, so their commutators with D vanish. The statement of this here is just that if you take a commutator of a thing with dimension 1 and a thing with dimension minus 1, you get a general inner combination of the things with dimension 0. Okay, so exercise. So let's define some operators L with L mu nu is M mu nu, L minus 1, 0 is D, L 0 mu is 1/2 P mu minus K mu, and L minus 1 mu is 1/2 P mu plus K mu. And L AB is antisymmetric. Show that LAB generates the group SOD plus 1, 1. Okay, so these are the group of rotations of Lorentz transformations in D plus 2-dimensional Minkowski space. And you had to know this was coming. I wrote down a bunch of commutation relations. What on earth are they? It turns out that they generate this group. And this will play a small role in these lectures. There is a way to exploit this fact to spectacular effect to do computations in conformal field theories, and that's called the embedding formalism, and João Penedones will talk about that next week. But for now, it's just an observation. Okay. Are there any questions at this point? Yes. Yeah, that will be a consequence of unitarity. For now, I'm just writing it so that we can interpret these commutation relations. What's wrong?
You said delta of k.
I think that's what I meant to say.
Right, but I mean.
Oh. Good point. All right, there's good meaning to this, but that will come later. Basically, delta doesn't have to be positive in this adjoint action on operators. It has to be positive on states. Other questions? Yes.
Could you define what a
Yes. Other questions? Good. Okay. So thank you for that question. I should have emphasized a little more what was going on. I'm trying to build things up from the minimal possible set of assumptions, and conservation of t and tracelessness of t is it. That's all we're going to assume, and we're going to get everything else from that. Okay, good. Okay, so we have a bunch of symmetry generators. They have this interesting algebra, and now we should use it. So the first thing that we can do is classify the operators in the theory using the symmetries. And we'll do this in stages. Let's first talk about Poincare representations. And just as a reminder, I'm in Euclidean signature, so by Poincare, the Poincare group, I really mean just Euclidean translations and rotations. Okay, so if all we have are Poincare generators, then it's natural to demand that our local operators have definite spin. So what this means is just that the commutator of a local operator at the origin with the rotation generators is given by some finite dimensional representation of SOD. So to be a little bit more explicit, if our operators have spin, they can have some index A, which takes values in some as an index of some SOD representation. And then the commutator with M just gives some matrix times O at the origin. Exercise. Show that the minus sign is consistent with S and M having the same, satisfying the same algebra. So that's just a quick thing you can check for yourself. But we can think of it as just a convention. Okay, so this is a natural thing to demand. And once we've demanded this, using simply the symmetries of the theory, we know how mu nu acts on an operator at any point x. And I'll be very explicit about this, just because it's a computation that will show up time and again in what we're doing. So to do this computation, so just to be clear, it's interesting to consider operators that are not at the origin. And so far, all I've said is what happens when M acts at the origin. So we now want to say how it acts on all the operators. And there's a useful shorthand for doing these kinds of computations. which has a secret hidden meaning that will be clear in the next lecture, which is to make the action of charges on operators by commutation implicit. Okay, so when I write QO, I mean the commutator of Q with O. And in path integral language, I mean I take O and I surround it with a topological surface operator. These are all the same things. And similarly, if I have some nested commutators, then this just becomes Q1, Q2, O. And in this language, I can freely use the commutation relations between these guys. Okay, and the reason this works, you can think of it as a consequence of the Jacobi identity. So this is something that you should check, that this notation is consistent. And more formally, it's just a statement that adjoint action gives a representation of an algebra. And another way to interpret it in path integral language is it just tells you how to rearrange topological surface operators past each other. So again, you can just think of this as being O surrounded by Q2 surrounded by Q1, and we can just move them past each other using the commutation relations. Okay, so all of these are equivalent, but this is this is very useful for doing computations. Okay, good. So mu nu with O not at the origin anymore. By our shorthand, we're going to write it like this. And O not at the origin is just translated by the translation generators. So this is e to the minus I p dot x O at the origin. Okay, and then what do we do? So some nice rewriting tricks. Let's just insert 1 on the left-hand side. And then suggestively group terms. Now we can use the Hausdorff formula. I think it's called that, which says that e to the a b e to the minus a is b plus a commutator b plus 1/2 a commutator b plus dot dot dot. Okay, so we take this thing, we replace it with a bunch of commutators. The first term is just mu nu. The next term will have some commutators of mu nu with p, and those are just given by various p's. So that's x mu p nu plus x nu p mu. And then we have commutators of p's with p's, which are just 0. So the thing truncates at second order. And that's just that. Okay, and now, all right, so we've assumed how, we know how mu nu acts at the origin. We can just replace that with our finite dimensional representation matrix. And the action of p's is just given by derivatives. So this is equal to minus I x mu d nu minus x nu d mu minus s mu nu O of x. And if you like, we could write this as minus little m mu nu plus S mu nu of x, where little m mu nu is the vector field that generates rotations. Okay, so this is something that you've probably seen in your quantum field theory textbooks, and we're just going to do it again and again to understand how conformal symmetries act on the operators of the theory. So the basic structure here is what's called an induced representation. Basically, you assume something about how a subgroup of your group acts, and then that using the algebra determines how the full group acts. And this is precisely what Raphael was talking about with the representations that particles live in. You can think in this case of the rotations around the origin as being sort of the little group for this computation. Okay. Good. So these are the consequences of Poincare symmetry using just the Poincare algebra. Let's now add scale symmetry. So here it's natural to demand that our operators are eigenvectors of dilatation acting at the origin. And the factor of I here for now is just a convention. As I said before, delta is called the dimension of O. And now exercise show that the commutator of D with O at x is equal to this differential operator acting on O of x. And the meaning of this differential operator is just that when you act with dilatation, you get an effect from moving the points, expanding the points around, and also the operator O has some intrinsic scaling associated to it. So there's an extra term that depends on delta. It's exactly the same as in the case of rotations. You can think of this thing as corresponding to moving the points with a rotation, and then the operator has some intrinsic spin itself. Okay, so this is already enough to fix a two-point function in a scale invariant theory. So let's consider a two-point function of operators O of x1, O1 of x1, O2 of x2. Actually, let me say x and y. So by translation and rotation invariance, this is just some function of x minus y. We'll assume that they're scalar operators for now. Okay, so how do I use the consequences of scale invariance? Well, what I do is I have my path integral. I have my two operators at x and y. The statement is that I should get 0 if I surround the whole thing with the dilatation operator. This is really a statement about the boundary conditions in which we're evaluating the path integral. The idea is that for an appropriate choice of boundary conditions, we can take D and we can kind of move it to the boundary and annihilate itself. That might sound a little bit weird, but in a CFT, it turns out it's a useful physical picture is to actually think about the theory as living on the sphere. So there's the origin, and there's the point at infinity. The conformal symmetries they just move the points around willy-nilly. There's nothing special about the point at infinity. So what you can imagine doing here is you start with D around the point at infinity, which obviously does nothing if there's no operator in infinity, and then you move it down to surround all the operators near 0. And what I mean by this picture is you can just, to demand this statement, you can just say that you've defined your theory by putting the path integral on a sphere. Okay? This just means we have scale invariant boundary conditions. So now, D is topological, so what do? We have X, and we have Y, and we can deform this surface to surround X and Y individually, and this just gives us a sum of the differential operators acting at X. And Y on F. This might have looked a little bit unfamiliar, but actually all I'm doing, if you, so exercise, interpret this statement in some quantization. And there you'll see it's a totally trivial statement about commutators. Okay, so just take this correlator, write it as some time-ordered product, and see what happens. All right, so the claim is that this is supposed to equal 0. And this means that f of x is just some constant over x to the delta 1 plus delta 2. Okay, so this is an example of actually using the symmetries of the theory to make predictions. Using conformal symmetry will make an even more refined prediction for this two-point function, but this one just depends on scale invariance of the theory. And you can already see here that it's unphysical to have negative delta. So if the deltas were negative, then you would have a two-point function of local operators that grows with distance, which violates cluster decomposition. So we'll actually prove later that the deltas are positive, but for now you can already see that it's bad if they're not. Let's see. I think that's a reasonable stopping point. We'll start next time with the full consequences of conformal invariance for the operators of the theory. So, thanks.